Good evening, everyone. Welcome to the official Open NLP Lab live broadcast room. I'm the rising tech star Izzy. First of all, Merry Christmas to everyone. Tonight in our live broadcast room, we will also bring you a tech Christmas gift. Thank you very much for coming. Tonight, we will start the pre-training of TransNormer LLM 15B. We will also live broadcast the entire pre-training process of the model, taking everyone from 0 to 1 to understand the pre-training of efficient language models. Tonight, our entire process will start with an introduction to Open NLP Lab. In the second part, we will introduce the efficient large language model TransNormer LLM, as well as the structure of this 15B model. In the third part, we will introduce the pre-training data for this session. In the fourth part, we will introduce the pre-training settings and estimated time for the 15B model. Following this, we will introduce the daily live broadcast content and planning. Finally, we will leave time for Q&A session. Open NLP Lab was established in 2021 as an international nonprofit scientific research organization, later affiliated with the Shanghai Artificial Intelligence Laboratory. Open NLP Lab currently has over 20 members. The research mainly focuses on three major directions: efficient sequence modeling, large language models, and understanding and generation of audiovisual language multimodality. Since our establishment, through the efforts of all members, we have published more than 20 papers on efficient sequence models and multimodality, covering almost all top AI conferences: TPAMI, ICLR, EMNLP, TMLR, NeurIPS, CVPR, ICCV, ECCV, AAAI, etc. We are also very honored to have received the best paper at the ICCV Workshop 2023. We have made significant progress and breakthroughs in the fields of efficient large language models and multimodal understanding and generation. Our research achievements in the field of efficient large language models include linear transformers, long convolutional sequence models, and linear recurrent neural networks, all of which have reached an international leading level. Our patents and research results are ahead of Stanford University's Flash Attention team and the RWKV team. Our team has also made pioneering research achievements in the field of multimodal understanding and generation. We proposed new audiovisual segmentation tasks and fine-grained audio-video description tasks, providing corresponding datasets. Among these, the method for the audiovisual segmentation task proposed by the Zhejiang University DCD Laboratory won the Best Paper Award at ACMMM 2023. Our official public account covers mainstream platforms, and we welcome everyone to follow us. We regularly update our lab's progress on WeChat and Twitter, as well as announce important events. You can also send us private messages through these two platforms. We respond to every message we receive. All of our codes and models will be open-sourced on GitHub, Hugging Face, and ModelScope. The code for our large language model, TransNormer LLM, can be found on GitHub, and the model weights can be found on Hugging Face and ModelScope. Our video dissemination platforms include Bilibili, YouTube, and TikTok. We post explanations of our papers and current mainstream papers, as well as other hardcore knowledge on these platforms. We also live stream our large model training on these platforms. We are planning to live stream even larger models, such as those with 30 billion and 70 billion parameters. We welcome everyone to pay close attention. In addition, we have an official website. OpenNLPlab.com.cn is our domain. We also publish original articles on Jihu, Medium, and Quora. Let's unveil today's protagonist, the efficient large language model, TransNormer LLM. TransNormer LLM is an optimization and development based on the TransNormer Foundation. It belongs to the category of efficient large language models as a linear transformer. It is well known that the complexity of the ordinary transformer is quadratic, meaning that as the sequence length increases, the time and memory consumption rise exponentially. The core idea of the linear transformer is to change the left multiplication of QKV to right multiplication through the kernel trick, thus reducing the theoretical computational complexity to linear. Before this, linear transformers could not match the speed and accuracy of the ordinary transformer. TransNormer LLM is the first model to apply optimizations in network structure, algorithm engineering, and distributed systems, thereby surpassing the transformer and other efficient transformer models, such as RetNet, in terms of speed and performance. We also conducted benchmark tests on mainstream efficient large language models, including Mamba, TransNormer LLM, HGRN, and TNN, and compared them with the mainstream transformer architecture Llama. We focused on training loss and speed on our own 30B subcorpus, with the experimental model parameters reaching 3B. As the graph shows, TransNormer LLM and Mamba achieved slightly lower PPL, perplexity, compared to Llama, with TransNormer LLM significantly faster than all previous methods. Experimental setup. For the 1B model, we used 16A880G GPUs, with a batch size of 12 per GPU. For the 3B model, we expanded to 32A880G GPUs with a batch size of 30 per GPU. The training context length was set to 2K. We previously mentioned that TransNormer LLM is the first to apply optimizations in network structure, algorithm engineering, and distributed systems. In terms of network structure, our optimizations include the design of position encoding, gating mechanisms, activation functions, and methods of tensor normalization. In algorithm engineering, we introduced lightning attention V1 and V2, optimizing the implementation of the attention operator, normalization functions, and more. In the distributed system, our optimizations include the implementation of tensor parallelism and model parallelism, among others. With all these optimizations, TransNormer LLM achieves faster speed, lower memory usage, and higher accuracy in both BF16 and FP16 setting, compared to the transformer architecture enhanced with flash attention 2. This is something that other efficient large models currently cannot achieve. TransNormer LLM possesses advantages in both training and inference. For the first time, we expanded the parameters of a linear transformer to 175 billion. We also compared it with mainstream scales enhanced with flash attention 2. On average, our training speed is 20% faster than flash attention transformer, and our perplexity, PPL, is 9% lower. In the left graph, we compared the speed and memory usage of the core attention algorithms of the models. This included lightning attention V2, flash attention 2, and the most common softmax attention. In terms of training speed, for tasks with up to 100,000 contexts, our attention module is up to 40 times faster than flash attention 2. In terms of training memory usage, for tasks with any length of context, our attention module has the same linear memory advantage as flash attention 2. TransNormer's greatest advantage lies in its constant inference speed, offering a significant efficiency advantage over the transformer in long sequence predictions. As shown in the graph below, our TransNormer LLM, RS, maintains a constant inference speed and memory usage even as sequence length increases. In contrast, the standard transformer and the standard transformer with KV cache optimization require several times to several tens of times more time and memory as the sequence length increases. Due to TransNormer's constant inference speed advantage, it achieves several times the efficiency improvement on long sequences, and the longer the sequence, the more significant the improvement. In our single A180G inference throughput test, our 7B model was able to process and complete 130 requests per minute, which is 4 times more than other models of the same 7B scale. Our model can process and complete 1080 tokens per second, which is 3 times more than other models of the 7B scale. The most important aspects of a large language model are its structure and pre-training data. The quality and quantity of pre-training data have a far greater impact on the final LLM's effectiveness than the model structure. Since the pre-training corpora of LLMs from various companies and research institutions are not publicly available, we independently collected a large amount of publicly accessible text from the Internet, totaling over 700 terabytes. We can categorize the data sources into 6 groups: academic writing, books, code, encyclopedia, filtered web pages, and others. The primary languages are English and Chinese, along with code, but also include other languages like Japanese and Arabic. As previously mentioned, the quality of pre-training data greatly influences the model, so we put considerable effort into data preprocessing. Specifically, our data preprocessing process includes 3 steps. 1. Rule-based filtering. 2. Duplicate data removal. 3. Self-cleaning filtering. Before being added to the training corpus, the cleaned corpus needs to be evaluated manually. After repeated data preprocessing, we selected 2.5 T tokens of high-quality data, which was then resampled to control the data ratio, resulting in our first batch of approximately 2 T tokens of high-quality pre-training data. The detailed distribution of the data can be referred to in our previous table and our paper. Let's introduce the TransNormer LLM-15B. This model has 15 billion parameters. It consists of 42 layers, with 40 attention heads and a total embedding size of 5,120. The right image shows the structure of a single layer. This model uses the TiToken tokenizer, with a total vocabulary size of about 100,000. The channel mixer employs Swish GLU, a further simplification on the GLU module, which means it doesn't use an activation function. The token mixer uses gate linear attention, GLA, which adds an output gate to the original norm linear attention. For position encoding, the first layer uses LRPE and exponential decay, while the subsequent layers only use exponential decay. During the actual training process, TransNormer-LLM-15B will be trained in 4 stages. In each training stage, data is sampled from our high-quality pre-training dataset according to the data ratio, totaling 1.3 T tokens trained, with an estimated training period of 3 months. We will use the Metaseq framework on an 80 GA100 cluster, employing FSDP, fully sharded data parallel, plus activation checkpointing techniques, with a global batch size of about 3.6 M tokens for pre-training. According to tests, TransNormer-LLM-15B achieves a TGS, tokens per GPU per second, of 1620 plus at a 6K sequence length, compared to Llama 2 to 13B's TGS of around 1500 at a 4K sequence length. During the training period of TransNormer-LLM-15B, we will live stream and share the entire process. We will open source including training curves, training weights, and benchmark test results. Throughout the process, we will synchronize metrics such as training loss, PPL, LR, and TGS. We will also provide real-time logs on WANDB, with links accessible on GitHub, Twitter, and WeChat. We will share intermediate model weights trained every 50 B tokens on Hugging Face and Model Scope. Additionally, we will share comprehensive evaluation results of the intermediate model weights trained every 50 B tokens. Feel free to ask any questions.